Hello. This is 1.5, so we're in college algebra here, and we have more on slope today. So let's get started. 1.5. Let me expand this so it fills up the screen. There we go. More about slope. In particular, it's the parallel and perpendicular issues. So my symbol for parallel will be the railroad tracks, and then my symbol for perpendicular will be the upside down T. Okay, so with regards to slope, if you have parallel lines, then the slope of the first line, I'll call m sub 1, will equal the slope of the second line. I'll call m sub 2. Then B, if they're perpendicular, the slopes are, what did they say, negative reciprocals of each other. In other words, if you multiply them together, you'll get -1. But you've probably been introduced to it, like if you have M1 is -2, then to find the slope that's perpendicular to it, what do? You take the negative of it and then flip it, right? So you would end up with 1/2. Okay, let's look at maybe one or two more of those. If your first slope is negative, let's say 2/5, then the perpendicular slope would be positive 5/2. So you just flip it again, and if your slope was, let's say, I don't know, 1/2, then the perpendicular slope would be what? Well, that would be negative, and then you have to flip it, so -2. So that's just like the first example, but in reverse, right? Okay, so let's take a look here. What you'll be tasked with doing is finding an equation of a line and either slope-intercept form or general form, such that the line will have some characteristics, right? It'll go through a point and it'll be parallel or perpendicular to some given line. Okay, and then they want you to create the equation of a line. So in my first set, they want the equation in this form y equals mx plus b, which we all know is slope-intercept form, right? Okay, so first, problem 5, or well, let's just keep it as an example because the numbers always change on us. Okay, my pen isn't working. There we go. Okay, so the line we want passes through the point was it -8, -10, and it's parallel, so let's say parallel to the line y equals -4x plus 3. Okay, so what we're going to be using to form the equation of a line is point slope form. Okay, and for point slope form you need two things, right? You need a point. First off, a point, we have the point, right? It's -8, -10. But then you also need a slope. Okay? And the slope we're going to get from the line that they gave us. So the line that they gave us has a slope -4. Okay? So that's what we want to make the slope of our new line, because parallel lines have the same slope, right? Okay, so then we could use the, what is that, point slope form. So y minus y1 equals m times x minus x1. Put in the information, so y minus -10 equals -4 times x minus -8. Okay, and then we just need to get it in y equals mx plus b form. So, you know, I like to clean stuff up a bit. This is x negative is positive, that sort of stuff. We got to distribute. X minus 32, and then And I'll move the 10 to the other side, and I think I got it. Negative 4x minus 42, and that would be our answer. Okay. Okay. Let's do one where the given line is perpendicular. Okay. So in this example, the line we want passes through negative 4, 2, and it is perpendicular to the line y equals 1/3 x plus 7. Okay. So again, we need two things. We need a point, which we have. It's negative 4, 2. And in WebAssign, or not WebAssign, but my math lab, they're sometimes they'll just give you a picture, right? They'll give you a picture, and the point is on the picture. You have to use the picture to find the point. It won't just be given to you like this. So hopefully that's not confusing. But anyways, there's the point, and then we need a slope, right? So for the slope of the line that's perpendicular to the one we want, that's sitting right here. Right? That's just from slope-intercept form. We know the slope's sitting there. So the slope of the given line is 1/3. So the slope of our line is the negative reciprocal. So you flip it and make it negative. So it'd be negative 3/1. In other words, negative 3. Okay. So then we could go to our point-slope form and start plugging stuff in. It's really easy to accidentally put things in the wrong place. So sometimes when I'm working, I like to put, this is x1, this is y1, just so I don't accidentally swap them or mix them up. Okay, because you get the wrong answer if you put them in the wrong place. Okay, you distribute there. And I need to add the 2 to both sides. Okay, and there's our answer. They'll also ask you questions like find the general form. So make sure you read the question and you give them the form that they want. So let's look at one of those. Okay. So this time I want to put it in the form, put answer in general form, and in our book, general form is the ax plus by plus c is 0, and usually they want you to get rid of the fractions. Okay, so we'll see that. I don't think there was any fraction. Maybe there are. I don't know. We'll see. Okay, so the line we want passes through. Sorry, just waking up here. Passes through the point 5, negative 9, and then the line we want is perpendicular to x plus 7y minus 12. So they're giving their line in general form as well. Okay, so again, we need two things. We need a point, and we have that. It's 5, negative 9. And then we need a slope. This is going to be a little more work, right? Because we can't just read the slope off of the given equation. We're going to have to put it into slope-intercept form. Okay, so I'm going to move the x and the 12 to the right-hand side. Just added, subtracted the x and added the 12. Okay, and then I'll have to divide everything by 7. Okay, so I'll have x is negative x over 7. Whoops, that's a y, not an x. That would be a mistake. Get rid of that. Y, and then plus 12 sevenths. Okay, so the slope in this case, call it m1, is negative 1/7. So the negative reciprocal, in other words, the slope that we want, will be positive 7/1, which is just 7. Okay. Okay, now we can plug everything into our slope-intercept form. Y minus y1 is m times x minus x1. Okay, this is x1, this is y1. And what do we get? Y minus negative 9 is 7. times x minus 5. Okay. This time we're not solving for y. What we want to do is get the x and the y and the constant on one side. Okay. So we'll have y plus 9 equals, and have to distribute, 7x minus 35. And then I'm going to move the y and the 9 to the right-hand side. Okay. So I'll have, if I flip-flop the sides then, okay, so I'll do it in steps. So here I have 0 equals 7x minus y, and then minus 35 minus 9 is minus 44. And then I'm going to flip-flop sides. Okay, so we like to put the variables and constants on the left side. And that's, you can always do that. You can always flip-flop sides. Okay, so there's the general form for the equation of a line that's perpendicular to the given line and goes to the point 5, negative 9. Okay. So again, I don't know if I've said it or made it clear, slopes are important because they represent rates of change. And a lot of stuff in physics and biology and chemistry can be noted in terms of rates of change. So every day, if you drive here, well, you used to have a commute and everything, but whenever you drive around, you have a rate of change, right? Miles per hour and that sort of thing. Okay. They say that these rates of change are the language of the universe, and that's why we study it. Okay. It's not just something we use to harass math students. It actually has importance. Okay. So slopes as a rate of change. And you spend a lot of time in mathematics studying slopes. Okay. Okay, so an example, and I think it's example 3 in the book. Let me get my book open. Let's see where it is. Yeah, it's on page 220. If you're looking, example 3, page 220. So the line graph, so they give you a graph, and it's a line graph for the number of women and men living alone. They want you to find the slope for the women part of the graph and then interpret the slope. So I'll try to draw it out here a little bit. There's the year on the x-axis, and we start at year 2000. Is at 0, and then 2002, and then all the way up to 2012. So it's going by 2s, 4, 6, 8, 10, and then finally 2012. And then on the y-axis, there's the number of people living alone. In particular, there's 2 versions, the male version and the female version. Okay. So for the it's in millions, and it's going by 3s. Okay, so we have 3 all the way up to 21. 3, 6, 9, 12, 15, 18, and 21. And then it starts for women in the year 2000. There's 15.5 million women living on. It's 3, 6, 9, 12. This is 15, so about 15.5. So let me mark that. 15. Whoops, 2000 is the x-coordinate. So we got 2000. 15.5 million women living alone. And then the year 2013, there's 18.6 million women alone. So 18.6, about right here. Okay, so in 2013, what did I say, 18.6 million? eyes are going. 18.6, yeah, okay. All right, so what did they want us to do first? Find the slope and I guess interpret it, right? Express the slope correct to 2 decimal places. Okay, so this should be relatively easy given the 2 points that we have. And yeah, so there's a line connecting these, sorry. Okay, so the slope will equal 18.6 minus 15.5 all over 2013 minus 2000. It's just x2, y2 minus y1 over x2 minus x1. And then that's, what is that, 3.1 all over 13. And that will be approximately 0.24. Okay, so as a rate of change, what is that? So it means for every increase, well, it's millions of women living alone per year, right? So in particular, this would be, because it's positive, it means it's increasing. So there are 0.24 million more women living alone every additional year. So the number of women living alone is increasing. So when you think about these rates, I think that and this, let me mark the units, million per year. When you think about rates, you kind of get lulled into this idea that rates all revolve around speed, right? Like your cars and stuff like that. But you could think of anything really as a rate of change. Like I don't know, just here this idea. This is like a social issue. You could apply ideas from physics in sociology. You can apply ideas from physics into any area you want, crime, yeah. So let's write up what this really means. It means every year there are 0.24 million more women living alone. Okay, so being able to interpret this, good thing. Okay, average rate of change. So there's this issue about average versus instantaneous, and you can see this all the time in your car. So when you look at your speedometer, that's kind of like an instantaneous rate of change. But the truth is, if you have like one of those cars where you can toggle the screen, it'll give you like your average rate. If I drove to work, my car may tell me I on average I went 34 miles per hour, but obviously I did not go 34 miles per hour the entire way to work, right? I was on the highway. I was probably going like 65 there. In town, I was going 25 there. So there's this idea, there's this average rate of change, but at exactly 9:05 in the morning, 9:05 a.m. in the morning, maybe I was going exactly 35 miles per hour. So that would be like an instantaneous rate of change. So these are important concepts in physics and therefore in other situations. So we want to kind of introduce that idea here. Okay, so average rate of change is what we're talking about with regards to the book and the section we're in. Okay. Of a function in particular. So if you're given a function, f of x, the average rate of change from, let's say, x1 to x2 is given by this kind of slope. It's basically just a slope formula, okay? So instead of putting m, we're going to put change in y all over change in x. Okay, that delta, that triangle there, that's a Greek letter, delta, and it just means change. And so delta y is change in y, delta x change in x. Okay. In the numerator, we have f of x2 minus f of x1, which is basically just like y2 minus y1 all over x2 minus x1. Okay, and in particular, if you looked at the graph, your function may not be a straight line, right? So usually with slopes, we're thinking of lines, but now we can kind of put a slope to something that looks like this, right? So on the average, going from, let's say, x1 to, I don't know, some other point, x2, so x1 and this is x2, we can kind of assign an average rate of change, right? So basically what you end up doing is finding the slope of that line right there that I just drew. Okay, so maybe this would be, this guy here is f of x1, and then the lower guy is f of x2. So it's a way of assigning slope to a line that has a bunch of curves in it. Okay. Alrighty then. Let's try some of the types of problems you'll see in WebAssign, or sorry, in MyMathLab. So find the average rate of change of the function f of x equals 6x, going from x1 equals 0 to x2 equals 4. Okay, all right, so our change in y over change in x is going to be f of 4 minus f of 0 all over 4 minus 0. Okay, and then for f of 4, we just plug the 4 into this thing. So 4 times 6 is 24, minus, and then f of 0, we just plug 0 into there. 6 times 0 is 0. All over 4 minus 0 is just 4. 24 minus 0 is 24 over 4. And then 24 divided by 4, 6. All right, let's try another one. Another example. F of x equals x squared minus 2x, going from x1 equals 3 to x2 equals 6. Okay, let's set it up. So change in y over change in x is f of 6 minus f of 3 all over 6 minus 3. So I'm plugging 6 into this thing. So that would be 36 minus 2 times 6 is 12, minus, plug 3 into this thing. So 3 squared is 9, minus 2 times 3 is 6. And all over 6 minus 3 is 3. So I need some order of operations here. 36 minus 12 is 24. Minus 9 minus 6 is 3 over 3. So you get 21 over 3, which is 7. Okay, okay, I think that's good enough. Let's look at one of the examples in the book with regards to, I think this was the injection of drugs. Okay, so this is example 5 in the book. If you have the book open. If not, I'll write it out for you. I'll read it out. When a person receives a drug injected into a muscle, the concentration of the drug in the body, measured in milligrams per 100 milliliters, is a function of the time elapsed after injection, measured in hours. Okay, so find the average rate of change in the drug's concentration between 3 and 7 hours. And they give us another graph, which I'll try to draw out as best I can. So we have time on the x-axis, and we're going by 2s all the way up to 12. 2, 4, 6, 8, 10, 12. Okay. On the y-axis, we have drug concentration in the blood, milligrams per 100 milliliters. So I'll just put drug concentration. And it's going by 0.01, so 1/100th, all the way up to 0.06. So 0.01, 0.02, 3, 4, 5, 6. 0.06, and it starts out in the bloodstream at 0, and then it spikes really quickly up to 3, 0.05. So this point is 3, 0.05. And then it starts falling. There's another 0.7, kind of 0.02. So 2, 4, 6, 7, 0.02. Okay, and the curve is kind of concaved down, and then kind of does an inflection type thing and goes concave up on us and starts kind of going to 0 over time. Okay. They want you to find the average rate of change going from between 3 and 7 hours. So just looking at the picture, if you were to think about the slope of the line that goes through these 2 points, which is called the secant line, that's what we're after. Okay, so it must be a negative value. Let's find it, right? So it's change in y all over change in x. So f of, and this function is literally f of x, right? So this is this first coordinate at the peak. We think of that as x1 comma f of x1. Okay. And then this guy is x2 comma f of x2. The lower point. So f of x2 is 0.02, f of x1 is 0.05, all over x2, which is 7, minus x1, which is 3. Okay, so we're going to get negative 0.03 all over 4, and then if you divide that, it'll be negative 0.0075. So the drug concentration is decreasing by 0.0075 milligrams per 100 milliliters. Okay, so milligrams per 100 milliliters per, what are the time units? Hours per hour. Okay. Okay, so let's write it out. The concentration is decreasing by 0.0075 milliliters per 100, milligrams per 100 milliliters per hour. Give myself a little more room. Okay. Okay. So getting back to physics, there's also obviously average velocity. That's probably the most common application of average rate of change. And so average velocity, how does that work? That's just going to be your change in position over the change in time. And for physics, they use the letter S for position. And then over T, that's my cursive letter S. If you're not familiar with cursive, that's what it looks like. Let's look at problem 20. So on page 226, I believe it is. Okay. Suppose a ball is rolling down a ramp, and the distance traveled by the ball is given by the function in each exercise, where t is in time in seconds after the ball is released, and s of t is measured in feet. For each given function, find the ball's average velocity going from, and it has A, B, C, and D. Okay, so we're going to do part A. The position of the ball is given by the function s of t, which equals 12t squared. Okay, and then we'll just do part A. They want to know the average rate of change going from t sub 1 equals 3 to t sub 2 equals 4. Okay. Why were the forefathers obsessed with rolling balls down ramps? Well, it has to do with free fall. and studying the effects of gravity on things. And back in the day, they didn't have cameras, so they couldn't like drop a ball off a building and then get like a high-speed camera and figure out how fast the ball is dropping from the building over time. So they needed to slow that process down. So what did they do? Well, instead of dropping a bowling ball off a building, off the Leaning Tower of Pisa or something, they used ramps to slow it down. And then they can study how fast things fall in kind of a controlled environment. So that's why they had those ramps. So that's why you'll see if you're taking math, they study things like pendulums and ramps. Okay, so they weren't crazy. Okay, they were very smart. When you think about it, how can I study something that's falling very fast? Well, you slow it down. You use a ramp. Okay, these guys were smart. Okay, anyways, average velocity then, change in s over change in t. So what is it? It's s of t sub 2 minus s of t sub 1 all over t sub 2 minus t sub 1. So let's do our substitutions. T sub 2 in this case is 4. T sub 1 is 3 all over 4 minus 3. And then substitute it into the S formula. So 12 times 4 squared, 12 times 16, minus 12 times 3 squared, which is 9. 4 minus 3 is 1. So we get what? Can factor out the 12, I guess. We have 16 minus 9. 16 minus 9 is 7. So that's 12 times 7. Which I could do in my head is 4, 8, 84. And the units were feet per second. Okay. So on the average, from t equals, from time 3 seconds to time 4 seconds, the average rate of change was 84 feet per second. Okay, great. We'll let you go, and we'll see you next time.